Good afternoon, everyone. It is my pleasure to welcome you to this new session of the 40 Under 40 lecture series on combustion. Today, we are very happy to welcome Professor XiaoCheng Mi. He's an assistant professor in the Power and Flow section, the Department of Mechanical Engineering at the Eindhoven University of Technology. He earned his PhD from the McGill University in Canada in 2018, and before joining TU Eindhoven in 2021, he had a postdoctoral position at the Cavendish Laboratory of University of Cambridge, where he worked and as well as in the Alternative Fuel Laboratory of McGill University. He has received the John Lee Young Investigator Award at ITER's 2019, and he was invited to the early career panel at the 40 International Symposium on Combustion. I was actually in the venue where you were in this panel, and also a combustion webinar. The research of XiaoCheng Mi actually focuses on the iron power cycle, detonation engines, and the hydrogen combustion safety. And I'm very happy that you will talk today about this new topic that is actually taking a lot of momentum. So we talk about enhancing iron powder combustor performance through fundamental insights. We look forward to your lecture and give you the floor. Thank you very much.
Yeah, thank you, Professor Parenti, for this nice opportunity, and also thank your team for organizing this series. I noticed this is actually going very well. Includes a lot of people, and it has been going on for quite a long time. That's a lot of effort. My talk today is about iron powder combustor. This is related to our group's current research focus, on iron power cycle. So without further ado, I will go into my introduction. So nowadays, if you listen to a lot of the combustion presentations, maybe people start with all this energy crisis plots and techno-economic stuff. So I'm not an economist, so I want to keep it simple. I just make three statements. So the first one is that nowadays the energy crisis is not due to the lack of renewable energy resources. We do have abundant resources that are renewable on our planet, but the problem is the availability of these renewable energy sources are intermittent in time and also geographically scattered. So what we need to do is to find good solutions for long-term storage and also long-distance transport for this renewable energy. And our solution here is called the iron power cycle. So what is about this idea? You can burn iron powder. These powder are like tens of microns of particles of iron. You can burn them in air, and the combustion releases heat, which can be used for power generation or electricity generation, or just as a heat itself. And the combustion doesn't release any CO2 because there's no carbon there. And after the combustion, you can recycle this iron oxide powders, also as micron-sized particles, and keep them. You can transport them to somewhere you can have easy and cheap access to renewable energy input. And with this renewable energy input, you can, for example, electrolyze water to generate hydrogen or directly use electricity to reduce iron oxide back to iron. So in such a way, you store the renewable energy as iron powder and transport it back to the end users. So this is the idea. And why iron? So we see several advantages of iron over some other, current developed energy carriers. For example, hydrogen and ammonia. So first of all, iron has a high energy density. So this is a small schematics shows, okay, if you want to contain this much of energy with one container of diesel, you need 5 times more volume of hydrogen, even liquefied compressed hydrogen. And ammonia is better because you pack the hydrogen to this molecule with the nitrogen atom but still the volumetric energy density is not as good as the conventional fossil fuels. But iron has a much better energy density in volume. It takes even less volume than conventional diesel to contain the same amount of energy. And nowadays, we also talk a lot about a lithium-ion battery, and this is the much of volume that you need to contain the same energy. Other advantages are, iron is safe to store and transport and has much lower fire and explosion risks, which is not the case for hydrogen. And also, iron is not toxic, not corrosive, and doesn't stink, which are the main drawbacks of ammonia. And also, a recent study shows that iron combustion gives very low NOx emissions burning in air. This is mainly due to the sole Zeldovich mechanism that is the only mechanism involved in iron combustion can produce NOx, and overall in the combustion chamber the temperature is relatively low. So this preliminary study shows that that's about 8 milligrams NOx per megajoule energy release, which is about 1 or even more than 1 order of magnitude smaller than that for other fuels. And why iron, not other metals? Nowadays, there are also people studying other metals like aluminum or magnesium for energy carrying energy storage, which are good, but iron has a certain advantages. The first one is iron combustion is non-volatile. Non-volatile means the combustion temperature of iron is lower than the boiling point of itself and also its oxide. This means during the combustion process, the particle remains in condensed phase, first in solid phase and later in liquid phase. And aluminum or magnesium, they have a relatively low melting and boiling points. And during the combustion process, the particle temperature can go above the boiling points. So this gives us a lot of evaporation, and most of the oxidation happens in vapor phase. And after this vapor phase oxidation, it forms a lot of nanoparticles, which are harder to be captured and recycled. So iron has the advantage of non-volatile combustion and a small amount of nanoparticle emissions. The other advantage is iron oxide after combustion can be reduced back to iron below the melting point. And that means this can be done either in solid phase or in a dissolved solution. And these are indeed the two technologies that our group are nowadays developing. One is using a relatively high temperature hydrogen-based reduction using a fluidized bed to reduce iron oxide back to iron. So what you are seeing here is a top view of a fluidized bed. So this bubbly feature is actually a hydrogen gas passing through the bed. In this way, you can reduce iron oxide back to iron. And another way, we can do direct electrolysis. So we directly use electricity. You apply the voltage over this electrolyte, which is an alkaline solution. You dissolve your iron oxide in there, and the iron can be deposited on the cathode surface. In such a way, you can achieve a much lower temperature electrolysis, even below 110 degrees Celsius. Okay, so this may sound a little bit provocative if you are working on hydrogen or ammonia. So that's not the message I try to send. We can calm down and then look at some fascinating phenomena of iron combustion. The first one is discrete combustion, because as I mentioned, iron combustion is non-volatile. So that means each energy source, each particle is like a discrete energy source in space. So if one particle releases energy, the heat takes time to propagate to reach its neighbor, and then in this way the flame or the combustion reaction front can propagate. So this is a small illustration using a reduced order model to show this discreteness of flame propagation. You see the heat is released and takes some time to reach the next particle. And if you zoom out, you just see a whole bunch of particles being ignited in a discrete way. And then the flame front structure looks very different from the conventional laminar flame that we are familiar with in gas phase. And how about the iron powder flame in real world? So this picture shows one of the first iron powder burner that was developed by a student team at TU Eindhoven. So what you are seeing here is not a 100% iron flame. It has a methane mixed with iron powder, so it's a hybrid flame. You can see iron powder can be fed here, and then through this dispersion system, you can stabilize a turbulent flame on top of the burner. And the later idea is the following, is the top injection iron powder burner. So you inject iron powder from the top, and there is also a swirl generator on top of this burner, and it makes a swirl inside this cylindrical chamber in such a way that iron powder moves in this tornado motion, which you can have a closer look here. And in such a way, the residence time of the iron particles can be increased, so they have enough time to combust and release the heat to ignite the later injected particles. So in such a way, you can maintain the flame without any other fuels in there. And this is one of the upscaling iron powder combustion system developed by a startup company Metalot near Eindhoven in the Netherlands. The picture you are seeing here is this MP200 pilot. And this one has reached 200 kilowatt. And they are also now testing a new pilot combustor MP500, which can reach even higher power output. So the schematics shows that there is a cylindrical burner, which is the upscale version of that tornado burner, where you inject particles from the top. While the particles are falling down, they are combusted and then release heat. The heat can go through the heat exchanger. And the particle can be settled at the bottom of the chamber. And you can see a human guy can remove this iron oxide powder for recycling. And some of the powder will be taken by the flue gas. So you need a secondary separation, which is the cyclone separator. And due to the centrifugal force inside the cyclone separator, you can further remove iron particles, iron oxide particles from it. And then the flue gas will go through a secondary heat exchanger to extract the heat from it. And this is a closer look of what is inside this industrial burner. So basically, the particles are injected downward with the gas, with air, combusted, and the particle can be settled down on the bottom. And there's also a heat exchanging system on the bottom surface to remove heat or keep the particles cool so they do not sinter. And the gas can flow back through these channels where there is a water cooling system. So you heat up you exchange heat with this system, and the gas go up, and then you will eventually go into this exit into the cyclone. And so far, you have probably, if you search the literature, there are already, quite a few papers on iron combustion published, but the only published document on industrial burner is actually recently became online. It's the thesis of one of our group's PhD student, Nick van Hooy. He published this thesis, which is mainly on the industrial scale burners, not the lab size. So if you want to know about the state of the art of this, please have a look at his thesis. So up to this point, you may start wonder, okay, you said a lot of good things about this iron power cycle. What is the overall energy efficiency, right? To be honest to you, so far, this energy efficiency is not yet very impressive. but this is the technology dependent. So let's look at it part by part. For this hydrogen-based high temperature reduction, the energy efficiency is not very good because you need to go through two steps. You need to first do water electrolysis to generate hydrogen, and then you do hydrogen reduction at high temperature, which you need to heat up the system. So the electricity to chemical energy stored into iron powder is around 40%, right? But this has a relatively higher TRL. That means we are already working on the upscaling of the technology. There's a better way of directly using electricity, as I mentioned in the previous slide. And this one can reach this Faraday efficiency, which means the electricity energy to iron deposition, almost 90%. This is already demonstrated in our lab, but the TRL is relatively low because we are still working on the lab scale reactor, not like at the industrial scale. But as a combustion scientist, I care about on the combustion side, right? Theoretically, if you burn a fuel, you can fully burn it. It can all go into heat, right? Thermodynamics allow us to do that. However, as you can find this in Nick's PhD thesis. So far, depending on the conditions, the heat, the iron chemical energy to heat efficiency varies from 50 to 80%. So not ideal, but theoretically, we should be able to 100% extract this amount of energy as a heat. And also please note this efficiency is calculated based on the oxidation degree of the material we collect after combustion. So this efficiency is not, the lack of efficiency is not due to the technology of a heat exchanger, right? And this makes us wonder why oxidation degree so far is so low in this technology, and how can we improve it? And for scientists, maybe not that engineering-like, I want to think about the fundamentals. So can all the particles injected into the chamber be ignited? And if the particle can be ignited, can they burn out? Can they reach the maximum oxidation degree or not? Okay, let's first think about the first question. And to investigate that, we did some tests with our lab scale tornado burner. And this time we use relatively large particles. The particle size you can see from this SAM image is around 100 micron. And the particles we use are irregular. So these are some magnetite ores that we take from some mining company, and then we use hydrogen to reduce them to metallic iron. And this is a closer look. You see the iron particle is not smooth, not spherical, and also it looks porous because of the hydrogen reduction. And if you burn these particles, if you burn them, then if the particle can be ignited successfully, it will go into liquid phase. And because of the surface tension in liquid phase, the product particle will look very spherical, like this one. But you can see in the product particles, there are a lot of particles are still irregular, which is overall similar to the unignited, uncombusted particles. This means that in these combusted particles, there is still a large portion of them fail to be ignited because they look irregular. They have never been into liquid phase. And this is consistent with the X-ray diffraction measurement. You see a lot of irregular particles, and indeed, you see there are still a large portion of iron remaining in the product particles. Okay, so this leads us to the thought that this ignition phenomena must occur in solid phase. The critical phenomena depends on the solid phase oxidation. Then we need to look at some basics about the solid phase iron oxidation. And in solid phase, iron can be oxidized to 3 different species. And the lowest one is FeO, or what we call woostite. And the intermediate one is magnetite. And then the most oxidized form is hematite, Fe2O3, right? And this is the picture taken from a metallurgy study back in the 1950s. It shows the oxide layer that grows on top of an iron surface, opposed to air, which is an oxidizing gas. You see that nearly 95% of this oxide layer is woostite, FeO. And then there is a thinner layer of magnetite, and a very, very thin layer on top, which is F2O3, hematite. And because of this multi-layer formation of iron oxide, its growth rate is actually depending on the iron ion diffusion rate through the oxide layer. So how fast it grows depends on how fast iron ions, Fe2 plus or Fe3 plus, transport across these 2 thicker layers. Of course, the thickest one or the most dominating one is FeO layer. Okay, so if this internal diffusion is the rate limiting mechanism, then we can actually come up with a reaction rate model to describe it. And the diffusion is mainly described by Fick's law. You know, this we also know this from heat and mass transfer that we study for gas phase combustion. And this Fick's law depends on the difference of concentration over the thickness of the oxide layer. So basically, this is the gradient of the concentration of the ion across the oxide layer. So it depends on the difference and inversely depend on the thickness of the oxide layer. The growth rate of oxide layer depends on the diffusivity times area, of course, and the gradient of concentration. And this can be written in this form. The derivative of oxide layer with respect to time equals to some parabolic rate law constant Kp divided by the thickness of the oxide layer. And this Kp is actually based on the diffusivity of the ion across this oxide layer. And this is known as the Wagner's theory, which gives a rise to parabolic rate law of oxide layer growth. And this Kp basically can be measured by fitting straight lines to the oxide layer growth over time at different temperatures. And it follows a certain Arrhenius form, which has the activation energy and also some pre-exponential factor, similar to the gas phase reaction kinetics, because this is an activated process. And by knowing such a oxidation rate in solid phase, we can actually build a model to simulate the ignition process of an iron particle. So we can build such a model by assuming this oxide layers is wrapping around a spherical particle. The growth rate depends on the parabolic rate law that we can get from the literature and using the experimental data to calibrate that. And then we can build a mass and the heat balance model for this spherical particle system. And here are some sample results. On the left, what you are seeing is a whole bunch of curves. They represent particle temperature as a function of time for different gas temperatures. So what is ignition? Ignition is basically you can let the particles heat release rate surpasses its heat loss rate. And if this happens, we say that we trigger particles thermal runaway, right? And if you change your gas temperature from a small value and you gradually increase it beyond some critical value, you can trigger particles thermal runaway. And this minimum temperature of the gas that can trigger particles thermal runaway is determined as the ignition temperature. So in such a way, by running this simulation, running the model in multiple ways with different gas temperature, we can determine ignition temperature theoretically. And here are some results. This is the ignition temperature as a function of a particle size. And the different curves shows the result for different initial oxide layer thickness. Right? You can see that the ignition temperature is highly dependent on the initial oxide thickness. You see that with this relatively large initial thickness, then you see that it requires a higher ignition temperature to trigger thermal runaway. Radiative heat transfer to the surrounding doesn't have a very major effects on the ignition temperature. So you see for large enough particles, actually in this range from 50 to 100 micron are the typical particle size range that we use for larger scale combustors. And in this range, you see that the ignition temperature is around 1080 to 1100. Right? And in these cases, we assume that the particle's initial temperature is the same as the gas temperature. So if the particle is injected into the chamber at room temperature, it would require a higher ignition temperature, which I'm going to show later in the slide.
60 millimeter. Okay.
Sorry?
They have different. For
Sorry?
that I saw something also similar. Wait. They will also like selling
Just
their.
a second, there is someone who is talking.
This one.
There is someone.
This
who
is nice. Yeah, I can get it.
Sorry, is that the question?
Something like
no,
this.
there is someone who is
Which
talking.
one should I get?
I should mute him. Just a second.
Okay, sorry. Yeah, I thought that was.
Please, everyone mutes himself. Huh? It's important. Okay, sorry.
Okay, yeah, no worries. Okay, I will continue. So this is a theoretical prediction. Okay, we need to experimental verification. So what I'm showing here on the left is an experiment also done in our group at the TU Eindhoven. It's a single particle ignition experiment. Basically, you can inject single ion particles in this middle tube. It's a very thin ceramic tube. And around it, this larger tube is a hot cold flow. So you can use electric heating elements to heat up the cold flow gas that has oxygen in there. And you can control the temperature of the cold flow gas. So in this way, you can determine the particle's ignition probability at the different temperatures. And here is the result. So what you are measuring is like you count the number of particles you observe, and if it's ignited, you count as ignition. So in such a way, after measuring for many particles, you get this ignition percentage as a function of cold flow temperature. So you see this ignition percentage goes from nearly 0 to nearly 100%, from 700 to 900 degrees Celsius over this 200-degree range. And this range seems to envelope what the theoretical prediction is. And in this case, I'm comparing it to the case that as I assume the particle has initially the same temperature as the gas. This is because the particles are carried with inert gas in this central tube. And before it encounters oxygen, it has already been heated to about the same temperature as the cold flow. But the thing is, like theoretically, it only tells us there's only one single value of ignition temperature, but experimentally it tells you a large range, right? So what gave a rise to this range of probability? So there are multiple factors that we are considering. First of all, the particles are not spherical, they're irregular and could also be partly porous. And also the particle may contain impurities, which changes its chemical and thermodynamic properties. Of course, the particle may have a different initial oxide layer thicknesses. And the last one is maybe the most relevant one to the larger scale combustor is the cold flow heating around the particle might be different. So the particle may experiences different heating processes as you go across this flow field. This I will elaborate further. So if the particle experiences different heating process, it may have the following result. So let's say if we consider there's one particle without ion particle without any oxide layer, and there is a certain ignition temperature that we predict with theory. And if the particle encounters this gas that is greater than this critical ignition temperature, then thermal runaway can happen. As I showed before, the particle can be ignited and burns in liquid phase. But if the particle encounters a gas that is below this critical value, so there's no ignition, and if you keep the particle at this gas temperature, which is already very high, but not enough to ignite the particle can still oxidize, right? So it will build up this oxide layer. And if you recall what I said before, the reaction rate is inversely proportional to the oxide layer. So as the particle builds up a thicker and thicker oxide layer, it will be even harder to be further ignited. So after it builds up this thick oxide layer, even you bring it up above the initially required ignition temperature, ignition may not happen. Yeah, so there are some studies, experimental and also theoretical, on the ignition temperature, but not much study has been done to the effect of the heating rate on the ignition temperature. And to this, I recently did a theoretical analysis. I just did a thought experiment. Let's say if you have a particle, 50 micron, initially at room temperature, and then you introduce that to air that is at 1100 K, which is actually below the critical ignition temperature. So the particle won't be able to ignite. You see here is the temperature of the particle of this black line is the particle temperature. So it will increase very rapidly to the gas temperature. It goes a bit above the gas temperature, but it cannot undergo thermal runaway, so it will cool down, eventually reach the same temperature as the gas. But the oxide layer keeps growing, right? This delta shows the ratio between the oxide layer thickness and the particle radius. So it keeps growing. And what this red curve tells you is the temporary required ignition temperature. So that means as the particle builds up its oxide layer, it requires a higher and higher temperature to further ignite it. So you see this is increasing. And in this graph, I summarize it with, I did a two comparison. One is, the size dependence. So you can see that this build up or this increase in required ignition temperature increases faster for smaller particles. These curves on top are for smaller particles. This is easy to understand because the smaller particles can be more easily can be heated up faster. So higher temperature leads to a higher oxide layer growth. And another interesting thing is that if you increase the gas temperature, it is a slope below the initially required ignition temperature, but you increase it is higher, it's getting closer to the ignition temperature. This oxide layer grows and the required ignition temperature increase is even faster. So this might be a little bit counterintuitive. You think, okay, you get even closer to the ignition temperature. Why you make it even harder to be ignited? That's because the oxide layer growth is also faster, right? So this is the key effect. And if we take this thought into what happens in a combustion chamber, you inject this particle into this reaction tube. As it falls down, it experiences some temperature gradient, and this will give particle a temperature change rate as it moves along the combustion chamber. So this is the summary of the graph I showed before. You have this curve shows the increase of ignition temperature over time as the particle builds up its oxide layer. And this straight lines indicates or somehow represents the gas temperature experiences, the gas temperature change rate experienced by the particle. So this more steeper slope means faster heating, and the shallower slope means slower heating. And if you can heat the particle very rapidly, it will encounter it will cross the ignition temperature curve at a lower value. That means if you can heat the particle faster, it's more likely you can ignite it. But if the particle experiences a much slower heating rate, it requires a much higher temperature to be ignited, and also takes a longer time to reach that ignition temperature. Right? So the conclusion on this is like a fast heating is required to achieve ignition. And after that, you also need to have a sufficient residence time in the combustion chamber to make sure the particle can complete its oxidation, which is the topic I'm going to talk a bit later. And another way to improve ion particle ignition maybe has something to do with the material properties. So in the previous work done by my colleague Conrad Hessels shows that the temperature of hydrogen reduction of iron oxide can influence the microstructure of the ion particles. You can see from the left to the right, we increase the reduction temperature from 400 to 800 degrees Celsius. And you can see the particle structure looks very different. It seems at higher reduction temperatures, the reduced ion particles are more porous, or the pore size are bigger. And we have the hypothesis that this larger pore size can facilitate oxygen penetration into the interior of the particle. In such a way, we increase the reactive surface area that can lead to a lower ignition temperature required. But we are right now doing the experimental investigation to verify our hypothesis. Okay, so that's about the first question, how can we ignite the particles? Then the second one is like, if the particle can be ignited, can we make sure they can fully burn out within the combustion chamber? And to know this, then we need to think about the liquid phase combustion after ignition, right? And this is some basic understanding. We burn these ion particles in our lab burner, and we can collect the product and do some further material characterizations. So these are some cross-sectional EBSD, electron backscattering diffraction, shows the phase distribution across the particle cross-section. The green area shows magnetite. So this, as I said before, this is the intermediate oxide product. The highest is hematite, is the red. You see that after the combustion in liquid phase, we can oxidize the particle mostly to magnetite. And then along some green boundaries or some cracks here, you see the formation of hematite. And why this is the case? this we need to take a look into the thermodynamic equilibrium phase diagram. So this phase diagram shows on the y-axis temperature, and in the x-axis is the mole fraction of oxygen in the whole in the Fe and O system. So above this line here, this is the liquid phase. N1 is liquid iron or relatively low oxygen containing liquid. N2 is normally considered as the liquid iron oxide. So under this dome, you have an immiscible mixture of L1 and L2. And this boundary over here is basically the liquid phase oxidation limit, because beyond it, liquid iron oxide cannot take any more oxygen from the gas into it, right? That means if you are burning this iron particle very rapidly in liquid phase, it should reach this boundary. And what does this boundary correspond in terms of stoichiometry? You need to lower it and look at here. So in solid phase, this vertical line is Fe3O4 magnetite. That means if you can by maximum oxidize your liquid phase iron particle to this boundary, it's about the same as the stoichiometry of Fe3O4. And that is why we are seeing Fe3O4 is the main product after combustion. And you can see this boundary actually also goes a little bit beyond Fe3O4, which means once it cools down, it actually contains more oxygen than the solid phase can hold. And this is why we see this kind of cavities formed, because the oxygen needs to be repelled out of it. And only in solid phase, if you keep it warm enough and supply oxygen, it can further oxidize to hematite, the highest oxide product. And then in liquid phase, we consider the particle might be limited by a few factors, so that so that the oxidation rate is governed by the interplay among these factors. So the first one is the boundary layer external diffusion of oxygen from the bulk gas to the iron particle surface. And then the surface chemosorption is the second process. And inside the particle, there is also internal transport of Fe and O ions. And of course, there's a reaction between Fe and oxygen. But we know this oxygen because in liquid phase, they are in ion form. So this reaction is very fast. Also, we assume at this very high temperature, the internal transport and the surface chemosorption can be also very fast. So in the very first model that we have for liquid phase iron combustion, we just assume that external diffusion is the only rate limiting factor. And how well this model does, let's see some results. We need to compare the results with some experimental measurement. So one experimental measurement is done by our former PhD student Daoguan Ning using laser ignited particle burning in air at room temperature. So this is the top view of the setup. The particle is injected in the center of this setup, ignited by laser, and the temperature will be monitored by this two-color pyrometry. And an independent experimental study was done by Panahi in US. They use this drop tube reactor. The particles are injected from the top going downward. The gas is already hot enough to ignite the particle due to this heating element. And the pyrometry can be looking down from the top to monitor the gas, the particle temperature history. So if we compare our modeling results to the experiments, we see the following. Again, this model is very simple. We assume that the internal transport is infinitely fast, and the liquid FeO, basically L2, is the main product in liquid phase. The surface absorption is 100%, also there's no limit there. And then the heat and mass transfer in the boundary layer is governed in the continuum regime. So on the left, you see this is a boundary resolved model done by Leon Theis using COMSOL to compare with the temperature history measured from this laser ignited particle case. You see the overall trend that matches pretty well. That means we are able to predict the temperature of the particle and also time scale of the combustion process. And then later, by Aki Fujinawa, we developed this zero-dimensional, even simpler iron particle combustion model, also matches the result very well, right? Both in time scale and the temperature. And of course, at higher oxygen concentrations, the results so far are not yet perfect. And for more details, you can look into Leon Theis' the PhD thesis. He looks into what are the effects and how to go beyond these assumptions. So here I won't elaborate on this point. But we can see that the iron particle combustion time are actually very short. And we can see that from Dao Guanning's result, if we burn iron in air, 21% oxygen, the reaction time, the overall combustion time is on the order of tens of milliseconds for these tens of micron-sized particles. And if you extend this rate law to larger particles up to 100, this is again the range of practical iron particles in industrial burner. The combustion time just extends to maybe about 100 or 150, 160 milliseconds, which is also not very long. And also, once the particle can be ignited, as demonstrated in these laser ignited experiments, the particle can sustain its combustion even in room temperature gas, right? So the particle can very hardly be quenched after ignition. And Dao Guan also did some further experiments using a gas environment at even lower oxygen concentration. Here you can see the particle can sustain its combustion even at 10% oxygen in the gas. And this, of course, will extend the combustion time. If we consider the same particle size, 50 to 100 microns, the combustion time goes up to 90 to 300 milliseconds. But also within a fraction of seconds, the particle can be burned out. So very likely in the realistic burners, because they are meters long, the particle should have enough residence time to burn out, because the combustion time after ignition is quite short. But there is only one phenomenon that we need to be careful with. Since in all these larger burners, particles are burning in turbulence, right? There is this phenomenon called the preferential concentration or clustering can happen of solid particles or liquid droplets in turbulence. And this normally happens when Stokes number is around 1. So if the Stokes number is very small, that means the particle's inertia is negligible to the fluid, the flow motion. So the particle behaves more like a tracker, it just follows the flow. And if the Stokes number is very large, that means the particle's inertia is much larger than the fluid motion, so that the particle behaves like a cannonballs. It doesn't sense the fluid. But if particle Stokes number occurs in this intermediate regime, some particles will follow certain eddies in the turbulence and form this clustering phenomenon. And this is uniquely important for iron dust combustion. The first reason is iron has a high density. So for the same size, it has a higher inertia, higher mass, right? And the second one, as I mentioned before, iron combustion is non-volatile. That means over the whole course of its combustion, it remains in this condensed phase. So not like a coal or biomass or other volatile solid fuels, initially it may be influenced by such a phenomena, but most of the heat release comes from gas phase reaction, right? So gas phase reaction doesn't, it's not affected no longer by the concentration, right? Preferential concentration. So this preferential concentration may have certain effects on the iron particle combustion. One thing is like locally the particle can be highly concentrated so that the particle can collide and then form agglomeration, right? This is one. And the second one is also because of this localized concentration. Locally, you can have a very fuel-rich region, and the iron particle may deplete locally the oxygen that is available. And this can lead to quenching or just a lower oxidation degree. So whether this may happen in reality or not, we don't have any in situ or very direct measurement yet, but we did some fundamental study based on CFD, right? We use this very fundamental way of constructing a box with a homogeneous isotropic turbulence, HIT, and you put particles in there. So you can see in this graph on the left is a random distribution or Poisson distribution. And if you apply HIT to this box, the turbulence will concentrate the particles into these localized clusters. So if we just set these two scenarios and let the iron particle combust in it, we can see the difference. And here are the difference. You can see here it shows on the top is the particle temperature as a function of time. There are three curves. The blue one is the Poisson or the random distribution, and the purple one is the 0D model. Just assume that all the particles react in the same way in this constant volume box. And the orange one is the temperature history of the clustered case. The particles start to burn after the clustered formed. So you can see indeed this clustered particle distribution have a significantly longer burn time. Similarly, can be seen in the gas temperature history, shown in this figure in the bottom. Okay. Then we see this clustering can indeed significantly elongate combustion time, but also this effect is not that significant to increase the combustion time by more than 1 order of magnitude. It's just several times longer, right? Okay, so we come back to the questions that we asked before. First of all, why oxidation degree is so low? And what we see from our lab scale burner and also the material characterization shows that many particles fail to be ignited. And theoretically, we showed this failure of ignition is due to the hindering effect of this growth of oxide layer, right? And actually, it's very less likely, this low oxidation degree is due to an insufficient residence time, because iron particle after ignition, the combustion time is very short. This turbulence caused the clustering can elongate the combustion time a little bit, but not make it longer by 1 order of magnitude. So it's still on the order of tens to maybe 100 milliseconds, which is very short. So what we can improve, I think that the main thing that we need to do is make sure the ignition rate as high as possible. So without telling you too much about the patentable content, the scientific message is to try to ignite the particle via fast heating. So before the oxide layer can be formed, or we can have a way to heat the particle in an inert way without letting it be oxidized. And once they are hot, you can inject them into the oxidizing environment. So these are the key features that we think we can do in our combustor to make sure we can get 100% energy to heat efficiency. So that's the story that I want to tell today. And there are quite a lot of publication already been done. What I can cover today is very minimum of it. I just want to make it a compact theory, compact story. I also didn't talk about that much about the economic side of this idea because I'm not an economist and I don't pretend to be one. So you can scan this QR code and find a collection of papers on the techno-economic analysis on iron power. So thank you all very much for your attention, and I would like to answer your questions.
Thank you very much for this very, very nice talk. I really enjoyed it very much. So the presentation is open for questions. Is there any question from the audience? Maybe I'll start with one myself. I don't know, maybe I lost it, or maybe you discussed it, but what is the expected cycle of utilizations for these particles?
Yeah.
How many, I mean, do you see an impact of the cycles of utilization on the efficiency of combustion? And if yes, how many regenerations you could do in theory?
Yeah, well, I think you are talking about the cyclability of the powders. Indeed, we did some research. I didn't include here. We try to just maintain, to try to check whether the particle properties remains the same. What we found is indeed after the first 2 or 3 cycles, the property may change quite a lot. This is mainly due to the initial particles may have different properties and impurities. But after 2 or 3 cycles, the property, for example, the size of the particle, and then the oxidation and the reduction degree of the successfully ignited particles will remain more or less stable. So that the property, the performance, we should expect to be stable. But this problem that I mentioned about the ignition is more like technology limited problem, so that we need to improve the technology to make sure that you don't have iron particle missed to be ignited, right?
Yeah.
So this is
this could have an impact on your ignition process, basically the one that you were describing before.
Yes. Yeah.
Thanks. Let's see if in the meantime there were people coming up with questions. Yeah, there is one. Zach, can you unmute yourself and ask a question?
All right, yeah. So thank you for the organizers. Thank you, XiaoCheng, for the great presentation. So actually, I have a couple of questions, and I would like to start with the when you was talking about the problem in ignition, the theoretical results you presented, where a particle fails to ignite and then forms a shell of or a layer of oxide, around the particle. I mean, do you have experimental evidence of this one?
Oh yeah, this we do. Yeah, I probably didn't include anything here. Here I have one in my slides. Maybe not the most maybe not the most evidence one, but we do have some more. I would say more direct evidence. This I just show you the one I just showed in my slides. So you see that this is actually a one that is failed to ignite. So because on the left side, these are the particle after going through the combustor, right? So you can see before, because of the reduction, you make the surface very porous. And in this one, you see the surface become smooth, like all the pores are gone, right?
Right, yeah.
So this is one of the evidence we make us believe this oxide layer is built up it covers.
Right.
And actually, there is a better evidence I didn't include in the slides. Is we do this cross-section view, and then we do EDX, electron diffraction scattering, and then we can see the elements. So indeed, those irregular particles after combustion, it's a thin oxide layer around it. Yeah.
Yeah.
This
Okay.
video is
So the question is not to challenge you, but rather, so so I started working on this recently in Nottingham Trent University in the UK, and so at low oxygen concentration, I got some particles burned, and others they form that layer. So I've been able to look at this, after doing the cross section and looking at the EDS. So all right. So this confirms what I currently found.
great.
Yeah.
Well, actually, you confirms my hypothesis.
Yeah.
Great.
Right. Brilliant. So the second question about the since most of particles we got are porous, and even after combustion and after inspecting the cross sections of the burnt particles, we still find pores inside the particle.
Right.
Do the pores go away after different cycles of reduction, or?
Oh, you mean the one that, because I think you are talking about the two different pores that I mentioned. What the pores from reduction is like, for example, this one I'm showing here. That's in the solid phase of iron particles that is produced by reduction, by hydrogen reduction, because the hydrogen reduction basically removes oxygen from it. So that's the molar volume of a metallic iron compared to the molar volume of oxide, across the stoichiometric ratio is less. So that after reduction, you always end up with a porous structure using hydrogen, right? But what we are seeing is like the pore size are different at different temperatures of reduction. So this is one porous structure that I mentioned. But I think what you are talking about later is the cavity or the pores like that occurs after combustion.
I meant that one, because
You
in
are
my
talking about this
particles,
one.
in my particles, I already have these in the raw particles, pure iron, and when I burn it, I still get the this large pores. So I was wondering if I do the one or two cycles of reduction, whether this will go away or may make it worse.
Right. Actually, it doesn't go, yes or no. Actually, it does go away every time you combust it. Because once you ignite it, when it goes into liquid phase, the surface tension will make it spherical or compact, as a compact sphere anyway. But this
not for
one,
most of the particles. Some of the particles, they go spherical, but when you do the cross section, you're gonna find some of these inside. They may not appear at the surface.
This in our theory right now, I think it will always be there in some particles, because in liquid phase, basically you can oxidize it beyond the stoichiometry of Fe3O4. And after you solidify it, immediately it can only form the oxide or stays in the lattice form of Fe3O4. So that means there is more oxygen in your solidified particle than the lattice of a magnetite can hold. And this oxygen has to go somewhere, right? And this is actually, there's a gasification process right upon the freezing of the particle. So we think that why we see this large cavity is actually due to this phenomenon. And there, what I said, like after the first few cycles, you do see some, larger fluctuation, and then it gets stabilized. This is mainly due to impurities. Impurities can also give you a cavity, but this, for example, if I have a carbon or sulfur, these are volatile impurities. And during this high temperature oxidation, they will form a gas phase product. And even the impurity mass percentage is very low because of the low density of the gas product. You can still make a big bubble inside the particle, and sometimes it can also cause this what we call a micro explosion, right? Basically shatter the particles.
Yeah.
So yeah, this can happen, but this kind of phenomena can go away after the first few cycles, because the combustion is actually purifying, it's removing these volatile impurities.
Impurities. Okay.
Yeah.
Yeah. Right.
Yeah.
Yeah. Thanks so much.
Yeah. Thank you. Thank you.
Thanks. So let's see if there are other questions. So I don't see any other question. In that case, I really would like to thank you again.
Yeah.
Thank you for this very nice talk. Thank you everyone for attending.
Yeah.
Everyone has a nice weekend and see you the next time.
Yeah. Thank you for organization. Bye bye.